So recall that an action potential occurs in one little part of the membrane and then causes or propagates and causes a new action potential to begin at a different part of the membrane a little bit further down. But if we're just considering, or we're just looking at the action potential that's occurring in that little part of the membrane, or one little part of the membrane, what we see is that the action potential itself actually inhibits a new action potential from beginning in that part of the membrane before that one has finished. So this phenomenon, or this event, is known as the refractory period. Okay? We're going to see two refractory periods. We're going to take a look at 2 points in time during an action potential where a new action potential is actually inhibited from beginning. Right? So we'll look at two refractory periods. The first one is called the absolute refractory period, where this is a point in time during an action potential where a new action potential will not occur or cannot occur no matter how strong our stimulus is that is trying to create that action potential, right? So a new action potential just won't happen during the absolute refractory period, okay? There's a point in time during an action potential, it's toward the end of that action potential, where a new action potential can occur, but it takes a very strong stimulus, right? That's called the relative refractory period, right? So like I said, this is a time during an action potential that's already occurring where a new action potential can occur, but the stimulus has to be very strong in order to get that new action potential to be created. So we'll take a look at some examples and see kind of what the refractory periods entail and what we're talking about here, right? So we'll start with the absolute refractory period, and on our graph of the uphill and downhill part of the action potential, recall that the uphill part of our action potential is called a depolarization when sodium enters the cell. The downhill part of our action potential is called a repolarization when potassium is leaving the cell, taking positive charge with it. And then we have this sort of dip below resting membrane voltage, or temporarily called hyperpolarization. Right? So when does the absolute refractory period occur? That is, this is a point in time when a new action potential cannot occur no matter how strong our stimulus is. So we can have the world's strongest stimulus going on at this particular part of the membrane, and it still won't create a new action potential. This one that's going on right now has to finish before a new one can be created, right? It essentially occurs between the start of the depolarization phase, that is the start of the uphill part of our action potential graph here, right? The upswing, the positive charge entering that particular part of the membrane because sodium is flooding into the cell. Okay, so it begins at the start of our depolarization phase, and it ends about halfway through our repolarization phase. So that's about halfway down the down slope of our action potential graph here. Okay, so what's going on at this point in time during the action potential that is actually inhibiting a new action potential from forming essentially on top of it, right? What's happening is that all of the voltage-gated sodium channels, that is all the channels that are contributing to the depolarization of our neuron, are either in the process of already opening or have already opened fully and are becoming inactivated at this point. So we can't physically open more voltage-gated sodium channels than there are in the membrane. So we can't create a new action potential when one's already opening. And recall that at the very top of the changeover from depolarization to repolarization, the voltage-gated sodium channels start to become inactivated. That is, that even if there is a stimulus, the channel still won't open and allow sodium into the cell. So even if there's a very strong stimulus, these channels aren't going to open again until they reset to their closed configuration, right? So that's the absolute refractory period. And in this particular graph here, those 2 time points that I mentioned, the start of our depolarization and halfway through our repolarization phase, are represented by this green highlighted region here. So that's all the absolute refractory period. Okay. We'll switch our attention, our focus now, to the relative refractory period. Okay. So that's this sort of darker blue region here that begins about halfway through our repolarization phase and ends at the end of the hyperpolarization phase when our membrane voltage returns back to resting membrane voltage, okay, at minus 70 millivolts, right? So what's going on here at this point in time, right? So what's going on here is that our voltage-gated potassium channels are open. Potassium is being allowed to leave the cell. Okay, so that means a positive charge is leaving the cell, moving across the plasma membrane. Okay. And voltage-gated sodium channels are beginning to return to their closed configuration, so that is, a new stimulus can open them, but not all of them have returned to their closed configuration. Some of them are still in their inactive configuration, which means that a stimulus isn't going to get them to open. Okay? So because of that, if a new action potential were to form during the relative refractory period, it would have to be very, very strong just to reach threshold. So, and the reason for that here is that because of the hyperpolarization phase, right? So the membrane voltage, remember, membrane voltage has to reach minus 55 millivolts, it has to reach threshold. Hyperpolarization represents a point in time when the membrane voltage is lower than resting. So that means that our membrane voltage has to come up to resting and then go up to threshold. So that just means more voltage, more distance, more voltage that needs to occur at our cell for a new action potential to happen. Okay. That's the relative refractory period. All right, so we'll take a look at the very end point here, which I have highlighted by a blue arrow here. So at this particular point in time, at the very end of our hyperpolarization phase, our blue arrow here represents the point in time when a neuron returns back to resting membrane voltage. So that means that a stimulus only needs to reach threshold, right? So it needs to go from minus 70 millivolts to minus 55 millivolts, which is our threshold, in order to create a new action potential there.